Nice to meet you here.
Yes, absolutely. Nice to meet you too.
Huh? Okay, now Sirajo, you can let's start.
All right,
Uh-huh.
just a minute. Let me open the slide. Okay. Can you see it?
I see it.
Okay, yes.
All right. Good morning, everybody. My name is Muhammad Siraj Abdullahi. Today I will give a pre-presentation of my thesis defense. The title of this talk is Coincidence Point and Lefschetz Numbers in Digital Topology. And my PhD advisor is Professor Dr. Umkam M. And my co-advisor is Associate Professor Dr. P. Christopher Stacker from Fairfield University from the USA. So this is an overview, or I can say an outline of what this talk is all about. I will first start with a general introduction of what I'm going to do during this presentation, and after that, then I will present the result we obtained by introducing partial BBS metric spaces and studying some fixed point theorems on the generalized metric space. And after that, I will also discuss about coincidence and common fixed points of several mappings, which is a study of coincidence and common fixed point on digital images. And lastly, the last part is just about digital Lefschetz numbers and approximate fixed points. To start with the introduction, Aaron.
Siraj, I am not getting your screen. What's happening? Not sharing your slides.
You cannot see my slides?
No. I don't know what's going on, but it's okay. I can.
Is anybody not seeing my slides?
Yeah, I see.
Okay,
I see it fine.
The slide is okay.
Maybe can you go out and come back, Professor? I don't know. Maybe that might be the reason. Okay, shall I continue? Yeah. So the general introduction is all about this. We are going to study fixed point theory, but the direction of this dissertation is two ways. The first part is studying fixed point theory on metric spaces, and the other one is studying fixed point theory on digital spaces. The first part deals with the study of given a generalized metric space. We are going to define a generalized or an extended metric space. Then we study some fixed point, existence of fixed point on the generalized metric space, and also common fixed point. And we are going to end this part with some nice illustrative examples. Then on the digital side, we have two directions. One is studying coincidence point set, and the other is studying Lefschetz numbers. On the coincidence point set, we are going to define what a coincident point set is, and also that of common fixed point. Then we also study what homotopy affect, how homotopy affects both coincident point set and their common fixed point set. And we will also show some other examples apart from the characterizations we are going to discuss. Then on the numbers, the simplicial Lefschetz number, which will help us find the approximate fixed point, which I will explain in the talk. And also the other Lefschetz number is called the cubical Lefschetz number, which will also help us find a kind of fixed point called n approximate fixed point. And we'll also throughout we will also discuss some examples. So to begin with, I would like to just remind ourselves what fixed point theory is all about. So fixed point theory is all about asking questions on what are the existence, what are the nature, what are the number of points that have this equation, that is f of x is equals to x. And we can easily see that graphically what we mean by fixed point, they are those points of this mapping f which intersect the principal diagonal line where y is equals to x. So the assumption on the functions or on the space x varies from practically none to quite difficult assumptions. For example, we have one of the fundamental results in Banach contraction principle in metric fixed point theory, which is Banach contraction principle, which is on conditions for the existence of such kind of point is the space has to be complete metric space and the function has to be contracted. Then if these two conditions are satisfied, he shows that this function will always have a unique fixed point. And he also provides a constructive method so that on how we can be able to achieve the point. And the other one is, which looks more topological, is the Brouwer fixed point theorem, which says that if we have a closed unit ball and we have a function from that closed unit ball itself, if that function is continuous, then we will have a fixed point. But in this case, it doesn't have to be necessarily unique, because if you take identity function, it's continuous, it has so many fixed points, so the fixed one here is not unique. So the other direction are the directions of Lefschetz, where Lefschetz, what he did is he introduced this number, LF, for any submap. He introduced a number called Lefschetz number. What he says is whenever that number is non-zero, whether it is positive or negative, non-zero, then any mapping that is homotopy to this function will definitely have a fixed point. So the main object in this direction is concerned with defining this set or this number, and this number is called the minimal number of fixed points for all mappings that are homotopy to this function f. But note that this number can be zero, and if it becomes zero, it means that we can find a function that is homotopy to f which does not have any fixed point. So another key result in Nelson theory or Lefschetz theory is the result of Nelson. But Nelson defined or introduced a number called Nelson number, where if this number is non-zero, it tells us every mapping homotopy to that function it has a fixed point. And also if I have two homotopy mappings, they will have the same Nelson number, or in other words, I can say the Nelson number is homotopy invariant. And it happens that this Nelson number will give us a clue on how to get the minimal number of fixed points. But the most interesting thing is if this Nelson number is exactly the minimal number, and if this happens, we call that space a vacant space. So this part I will try to introduce a new definition of a metric space, which generalizes many metric notions, and then I will study some fixed point theory related to this. So this theorem 2.1 is a generalization of metric notions in many directions. One of them is that of Mitrovic and Radonovich in 2017, and that of Matthews in 1994, where he defined the partial metric. The difference between this definition and that of Matthews is that the triangular inequality here is not our triangular inequality, that is item number 4, is different from its own. What he used the classical metric triangular inequality, but here we have some additional conditions, that we have this S that has to be greater than 1, and we also have this many number. We have more than two terms. So, but if this our definition, in our definition, if xy is equals to 0, then it means that x is equals to y, but the converse is not necessarily true. For example, if we define our set x to be just a, b, and c, the set of a, b, and c, we can define a mapping in this order, so that this mapping will satisfy the conditions of this theorem definition 2.1, and if it does, we will have this map. Sorry, we will have this to be partial B2 4/3 metric space. What I mean by this is that here my V is going to be 2, and my S is going to be 4/3, which is greater than 1. So, but this function will not give us a partial 2 4/, sorry, will not give us B2 4/3 metric, and it will not give us partial B2 1 metric. So, as a remark, we present this, and what I mean by this is, if our V is equals to 1 and S is equals to 1 in our own definition, then our definition will reduce to partial metric space of Matthews. And if our V is equals to 1 and S takes any number, then we'll end up having partial B metric space of Shukla. And also, if we have V is equals to 2 and we have S is equals to 1, we'll end up having partial rectangular metric space defined by the same author, Shukla. And other cases that were not existence to the best of our ability is partial B2S, which it will be called partial rectangular B metric space, and the partial BV1 metric space, which is partial B generalized metric space. So the topology on this space is defined in this fashion. If we are going to define an open ball in this order, the reason is, in this setting, the distance between x and itself might be a non-negative, so it might be non-zero. That is why we have this term in the ball. So if this term equals 0, then the whole definition of this ball will reduce to the classical definition of ball in metric topology. So, but it happens that this topology is not compatible with the metric, usual metric topology. We will see that using this this example, that if we have a set A, so the X to be the union of A union B, where A is just the set that contains this 1/n, the sequence, and B contains only 0, 2, and 4, then we can define a function in this order, so that this function will be B3 2 metric space, whereby this is the coefficient of the B metric space S, which is equals to 2 in this case, and it is greater than 1. So this also is not B3 2 metric space, and it is not partial B3 1 metric space. Why is that? Is because in the first case, the distance between the point 0, 0 is not 0. If it is 0, then we will say it is B3 2 metric. But since it is not 0, then it is not B3 2 metric space. And also, the reason why it is not B3 1 metric is because it fails to satisfy the triangular inequality analog of this definition. So with reference to this definition, we come to terms with this. We know that any open ball in this direction need not be an open set, which is contrary to what we have in usual metric topology. Why? Because we have this ball that is not open. Why is it not open? Is because we have this inequality. We doesn't have any C that will give us this kind of inequality or inclusion. And also the limits of a sequence in this metric space is not unique. Why? Because we have a sequence that converges to different limits. And also the convergence of sequence in this need not be Cauchy. We have an example why it is not Cauchy. And also we have a situation whereby the partial BBS metric need not be a Hausdorff metric space. So here I will present the first main result of this direction, which is like a variant of Banach contraction principle. And what we have is that a similar way of constructing a Banach variant, where we will assume that our space is complete, and we will assume that our mapping T satisfy the Banach contraction with contraction constant between 0 to 1, and our else has to be greater than 1. If we have this, then we end up having a unique fixed point. Another theorem we study is the Rich contraction, which is a generalization of a Banach contraction, and we found that any complete partial BBS metric space that satisfy the Rich contractive condition under these additional assumptions will end up having a unique fixed point. For example, we have set up this example to show that yes, our theorem is valid to support it. And what we do is we define the metric in this fashion, and we define our mapping to be just 0 if x is equals to 6, otherwise it will be 1. And this function t satisfy both 1 and 2. And since it satisfies both 1 and 2, and all the other assumptions of this previous this theorem are satisfied, then by those theorem we know that we will definitely have an existence of a unique fixed point, and that fixed point happens to be the point x equals to 1. So when we have this lambda i's, some of them going to 0, then the theorem 2.9 will reduce to many results in the literature. So another thing also we consider in this direction is the notion of common fixed point on partial BBS metric space. And the theorem we focus on is the Jung theorem, and we give the Jung theorem variant in partial BBS metric space as this. And we show that if this condition is satisfied and the function I is continuous, then T and I have a unique common fixed point. So as a consequence of this theorem, we know that even if we exclude the condition that I has to be continuous, this theorem will still hold. And this theorem generalizes many notions like previous theorem, generalizes many notions of many theorems in the literature. And also this theorem gives a complete solution to an open problem one raised by George in his paper in 2015. So Now we are going to move to the digital topological setting, and I'm going to talk about the coincidence and common fixed point of several mappings in this direction. But I will begin with what a definition of a digital image is. So a digital image is just a set of finite number of pixels that has particular value and particular uh, position. So we can view this picture as a two-dimensional digital image, whereby the pixels will be the element of that digital object, and where the white background will regard it as just the background of the image. So this study of digital image was initiated by Azrael Rosenfeld in the early 1970s, where he called it digital topology. And the reason why he introduced this is to give theoretical backings to some of the image processing operations they do study. Because already when he introduced the term digital topology, people had been already working with digital images operations like image thinning, image segmentation, and what have you. So the way he modeled this image is he viewed the pixels uh, as the vertex, and the relation between two pixels as an edge. And in this case, if we view an object in this case, we can view it as a graph, and that's what we follow in this study. For example, if we have two-dimensional image, in two-dimensional image we have two chances we can make an image a graph. One is by considering direct neighbors of pixels. In this picture, by this point, I mean these are pixels, the dots are pixels, while the line connecting them are the adjacency, the relationship between them. So we have two ways, whether we go directly, and in that case we are going any point, in that case we'll have only for neighbors. And the other one is, apart from going directly, we are allowed to go diagonal. And if we are allowed to go diagonal, we also have additional 4 chances. And cumulatively, we will end up having, for any point in this setup, we'll end up having 8 neighbors. Similarly, in the 3 dimension, we will have 6 adjacency, 18 adjacency, and 26 adjacency. So I would like to just share with you the digital concept of continuity, which is almost similar to the classical concept of continuity, but in this case, the aim of our continuous function is just to preserve the connectivity between the digital image x and y. What I mean by this is, for any two points that are close enough in x, their function would be close enough in y. And also in 1999, Boxer introduced this definition of homotopy, which is a function that satisfies these 3 conditions. And also I'm going to just remind us of what a digital null homotopy is. That is, a function is called digital null homotopy if it is digitally homotopic to a constant function. And if if the identity mapping is digitally null homotopic, then we call that image digitally contractible. And also in 2019, Boxer and Stacker introduced a function called rigid, a notion called rigid. What they have is, we call a function rigid if we cannot find any other continuous function which is homotopy to that function. And if this function happens to be an identity function, then we say the whole set is rigid. So now we recall that in a topological space, in a classical topology, topological space is said to have the fixed point property whenever every continuous function on that set has a fixed point. So a similar definition appeared in digital topology, but it happens that this notion of fixed point theory is not fixed point property is not interesting in digital setting. Why? Is because the only image that satisfy this condition is a single point image, and this renders this direction almost useless. So here I will try to introduce how we define the coincident point set. By a coincident point set, we mean a set of points in X such that the function f1 up to fi are all equal. So whenever we deform these functions by a homotopy, the shape and the size of this set changes. But in this study, we are interested in only the size of this set. And one possible measure of this set is the minimum number of coincidence points, which is defined as this, which is we are going to look at all those functions functions g1 to gi, such that g1 is homotopic to f1 and g2 is homotopic to f2 up to gi homotopic to fi. Then we'll check the cardinality of the coincidence element in that sense, and that will give us the minimal coincidence number. So here I present a theorem which basically tells us that isomorphism preserves the number of coincidence functions. All right. The proposition 3.6, what it tells us that if we have X and Y to be connected images, and the condition is if Y has more than one element, then it is always possible to obtain the coincidence point of the functions f1 up to fi to be empty for some continuous mapping f1 up to fi. Another proposition here is what will happen if the the cardinality of the image y is equals to 1. If this happens, then the set, instead of to be an empty set, it will be the whole set X. One example is this. If we consider this is a function whereby we can define a function, a constant function that will map the whole of X to say this point Y, and we have another function that will map the whole of X to say Y2. So we can see that these two constant functions, they are continuous, and if we take their coincidences, they will be 0. Why? Because this image Y contains more than one element. And if it only has one element, so we only have one continuous function on it, which is the constant function that goes to the point X. And in that case, if we do the coincidences of the of same mapping, we will end up having the whole set X. So another thing we consider in this direction is that we try to see some classical results in topology and see if those results will still hold in digital setting. And one of them is a result by Stacker that says if we have X and Y as a compact manifold, so the X is a topological space and Y is a compact manifold of the same dimension, and we have some mappings between X to Y, from X to Y, then this mapping can always be changed by a homotopy so that the coincidence of those mappings is empty. So one natural question in digital topology is that, can we have a similar theorem of Stacker in digital topology? Can we always have this to be equal to empty by a homotopy? And the answer to that is no, because when we allow our X to be a rigid image and we allow our function to be self-mapped, then the coincidence of, for example, this 3 identity is not going to be empty. Why is that? Is because if X is rigid, we know their identity is not homotopy to any function except itself, and because of that, we cannot reduce the coincidence of this set to become empty. So to continue in this direction, we define what we call this coincidence spectrum of the mappings F1 up to Fi, where I takes any number greater than or equals to 2. And this number will give us the cardinality of the coincidence set of functions F1 up to Fi. And more broadly, we will gather all those points, we take their union, and we call it the CS infinity xy. So as a special case, when we have x the same as y, then instead of using CSI xy, we'll simply call it CSI x. And similarly, we will define the collective coincidence point spectrum as CS infinity x. So as a corollary, now that we define what the coincidence spectrum is, as a corollary to theorem 3.5, we have this result that says that isomorphism preserves the coincidence point spectrum of this mappings of this set. Sorry. Please pardon me, I think something happens to my slide. So the next result is, if we have 2 digital images, we found that this number, that is the cardinality of X, is always contained in any coincidence spectrum. And additionally, if the cardinality of Y is greater than 1, then 0 is always contained in the coincidence point spectrum. And also, we have this theorem, and what this theorem tells us is that if we have an image that have n elements, and we have Y having at least one pair of adjacent points, then the coincident point, when we take I to be equal to 2, is going to be the whole full spectrum. That is from 0, 1 up to the cardinality of the image X. Here I present another theorem that says that the coincidence spectrum of I number of mappings is contained in the coincidence spectrum of I plus 1 number of mappings. And additionally, if Y contains at least one pair of adjacent points, then these two are the same. So whenever we have Y having at least one pair of adjacent points, then we know that for any I, the coincidence spectrum is the same. And one scenario we also consider is what will happen if we take a subset of X. So if A is a subset that is connected, then the coincidence spectrum of A will always be contained in the coincidence spectrum of X. And here we have a theorem that tells us a relationship between Fx and CAS of X. By Fx, I mean the fixed point spectrum is always contained in the coincidence point spectrum between 2 mappings. But another interesting relationship, interesting question that we shall ask is, what is the relationship between the fixed point spectrum and the coincidence fixed point spectrum when we vary the x and y? And this we'll see in this example. Our x here is this set, and our y is this set. So you can see that this is a subset of x, y is a subset of x. But by a result of Boxer and Starker, they have calculated the coincidence, sorry, the fixed point spectrum of this image to be to be a full spectrum except 7. 7 is not part of this fixed point spectrum. So, but by our theorem 3.13, we found that if y have at least one pair of coincidence point, so the one pair of adjacent points, then the CS xy will always be the same as from 0 to 8. That is, it is going to be a full spectrum. So now additionally, if we consider what will happen if we let Z to be just a single point image, and if we let Z to be a single point image by proposition 3.7, we know that this term is going to be only 8. That is the cardinality of this image, number of points in this image. And therefore, from this example, we can see that this CS, the coincidence spectrum of two mappings, is different from the fixed point spectrum, and it's also different from this when we consider Z to be only 1 point. So now we want to consider some situations. What will happen if X maybe say is connected and Y is totally disconnected? And we found out that if we have these conditions that X is a connected digital image and Y is totally disconnected. By totally disconnected, I mean the point in Y, they are far away from each other. What I mean is that we doesn't have any point that is adjacent to one another. And in that case, the coincidence point for all I is going to be only a set that contains 0 and the cardinality of the image X. But one interesting thing is that if we allow X to be also totally disconnected, for example, if we take X and Y to be two non-adjacent points, just only 2 points that are not adjacent to each other. X is X is an image that has only 2 points and they are not adjacent to one another, while also they are set of 2 points that are not adjacent. Then we can see that the spectrum will change, because we'll also have the introduction of 1 as an additional element. That's just because we consider X to also be totally disconnected. And in summary, what I'm going to do, this result is just like a summary of what I have discussed. That if we have two digital images X and Y, then their coincidence spectrum for any point is the same for all I, if any of the following is satisfied. One is if X is connected and Y is totally disconnected, and also when X is disconnected. The second case is when X is connected and Y has at least one pair of adjacent point. And we also see that whenever we have Y to be a single point image, we always have the coincidence spectrum to be the cardinality of X, which means that for all I, the coincidence spectrum will be the same. So one thing we are not sure is that we think that this is different from this, that is a coincidence of I mappings would be different from coincidence of I plus 1 mapping is that when X is disconnected and Y is totally disconnected. And because we are unable to prove this theorem, we term it as a conjecture. But we conjectured that even in that case, this coincidence point spectrum will be the same for all I greater than or equal to 2. So similar to the coincidence notions, we also introduced briefly the notion of common fixed point, where we define first what a common fixed point set is, which is defined by 4, and we also define the minimum number of common fixed point, which is this, and also we define the common fixed point spectrum as this, and more broadly, similar to what I have done in coincidence point, we define the union of all this common fixed point spectrum as CFS infinity X. But we can also view this definition of common fixed point just as simply as coincidence. But in this case, we are going to allow the Fi to be equal to identity. And if you allow Fi to be identity, then the coincidence between the function f1 up to Fi minus 1 will be the same as the common fixed point set. So, and one thing we remark is that if we have all these functions to be f, then an Fi to be identity, then the coincidence of these functions and identity will just reduce to the notion of the fixed point set. So similar to what transpired in the previous part, we also show that the isomorphism will preserve the number of common fixed point sets, and also it will preserve the homotopy common fixed point spectrum. And also, if we have a subset, it is homotopy common fixed point set will be contained in the common fixed point spectrum of the whole set X. And as a remark, whenever we have this common fixed point between a function and itself, this will be the same as the fixed point of the function f. And it is easily seen that the fixed point set is always contained in the common fixed point set. Here we define a homotopy common fixed point spectrum of some mappings f1 up to fi as this, and we have this question: what will happen if I have two mappings f1, f2, and all these mappings happens to be f? Because we have seen that in this case, if we have ff, the whole thing will reduce to the fixed point of f. So the question is, what will happen to the minimal number of common fixed point f1, f2? That is ff. Maybe I think it will be better if I write it ff. And also the homotopy common fixed point, will it reduce to the homotopy fixed point spectrum? And this is the common fixed point spectrum, and will it be the same as the fixed point spectrum? And if we consider this example, which is an image X in Z3, we consider this as three-dimensional image, then it was shown that the homotopy spectrum of any function f is the same as the fixed point spectrum. And from this paper by Boxer and Stacker, they have shown that it is this set without having 7. But by theorem 3.13, we can easily have this to be equals to 0 to 8, that is full spectrum, because this has at least one pair of adjacent point, and we know that the function, if we are talking about common fixed point, we are going to map this set X into itself, and by that scenario we end up having the homotopy common fixed point set of this function to be the whole spectrum, and also the the common fixed point spectrum to be the whole spectrum. So therefore, we can conclude that this, even if when the function ff, we have the function ff, this homotopy common fixed point spectrum will not reduce to the fixed point spectrum, and also common fixed point spectrum will not reduce to the fixed point spectrum. Now I will introduce a homotopy coincidence point spectrum, which is almost similar to how I define common fixed point, homotopy common fixed point spectrum. And we found out that the minimum number of this, the minimum number of coincidence point is always a minimum of this homotopy common fixed point spectrum. And we know that the minimum number and the homotopy coincidence point spectrum, they are homotopy invariant for any mapping on our image X. Another thing we consider is similar to what we have in the previous part, but you can see that the homotopy coincidence of I mappings is always contained in the homotopy spectrum of I plus 1 mapping. And for example, if we have a digital image to be rigid and we have an identity mapping, we have I number of identity mapping, and we have I plus 1 number of identity mapping. In this case, this inclusion is equality. Why? Because the whole of the set will be only the number of the element in X. And one result we have is that whenever we suppose our image is rigid and we have any continuous function f, then the homotopy common fixed point spectrum of the two mappings between f and identity will reduce to the fixed point spectrum of the function f, and the minimal coincidence number between the two functions will reduce to the minimal fixed number of fixed point of the function f. So another classical result we consider and try to give it is digital analog is the result by Brooks, which says that if we have two topological spaces, and we have two functions that are homotopy, f prime is homotopy to f, g prime is homotopy to g, then we can always have another function f prime prime which is homotopy to f, such that this coincidence set is the same as this coincidence set. So what we'll do is we want to try to see if we are allowed to have this kind of nice result in this direction. But before I move to that, to avoid confusion, when we allow only one of the mapping, because in this case we are allowing both mappings to be changed by a homotopy, but whenever we allow only one, the second map to be deformed, when we allow the second map to be deformed by a homotopy, while keeping the fixed one fixed, we change the notation of this set by introducing an asterisk at the top of the notation. For example, if we see anything, any set MC star F1, F2, it means the minimum coincidence number such that G1 is allowed to be changed by homotopy. From here, you can see that, while the function F2 is remain fixed. And as a corollary to this theorem 3.32, Brooks has this result that if we deform only one of the two mappings, then the minimal coincidence number will not change. So, but in our digital setting, if we allow f and x to be sub-mappings on the digital image x, but we have an additional condition on the function g to be rigid, then by corollary 3.33, by the above corollary, this is going to be the same as this. That is, even if we change only one, it will be the same as the minimum coincidence number between the two functions. And one example we consider is this following example, that we have a digital cycle. By digital cycle, we mean a digital image that in which every point is exactly adjacent to only two neighbors. That is, if I take this, it's only adjacent to two neighbors. Any point is only adjacent to exactly two neighbors. And it happens that if we take identity mapping and we also take a constant mapping on this image, the coincidence, the number of elements in the coincidence set of this identity and the constant mapping will always be equals to 1. Because suppose this is just identity mapping, and I have another continuous function that will just map everything to 1, then we know that it's only one that we will only have one of them that will be fixed, and we end up having one element, and the cardinality will always be 1. But what will happen if we are allowed to deform only the identity mapping? And if we are allowed to deform the identity mapping, by some homotopy, then this coincidence set will be also equals to 1. Why? Because any function that is, it was shown in A, that is by Boxer and Stacker, that any mapping that is homotopic to identity on a digital cycle must be a rotation. And if it is a rotation, then if we do a coincidence between a rotation map and the constant function, will end up having only one element, and at the end we have one number of elements, and the whole of this homotopy coincidence spectrum will be only a singleton containing number 1. But however, if we are allowed to change both mappings, that is, we are allowed to change identity and we are allowed to change constant mapping, then it was shown also in the same paper that if a function is homotopic to a constant, then that function will have this number of fixed points, and by this number of fixed points, we'll end up having the homotopy coincidence spectrum between the identity and C when we allow two of them to be changed by homotopy to be the set 0, 1, 2, and 3. And moreover, what will happen if we change the position of these two mappings? Instead of identity and C, we use C and identity. And if we do that, both changing 1 and changing 2 will result in us having 0, 1, 2, and 3. So we can see that when we change the position, it matters, because here we change it and we end up having both of them the same and equals to 0, 1, 2, and 3. But in this case, when we have this, we have one set equals 1 containing only 1 and one set containing 4 elements. Now we also study one special number called step coincidence number, which is almost the same as the minimum number of coincidence points, but in this case the function is going to be repeated, like MC F F F. We don't have F1, F2, F3. We have only one F, then we repeat it J number of times. And another special case of this is when we take this function to only be the identity mapping. And if we take this to be identity mapping, we'll end up having this set. And for instance, if J is equals to 2 and J is equals to 3, we have J is equals to 2, we have this to be equals to MC ID ID. And if J is equals to 3, we have the minimum coincidence number between the 3 identity mappings. But we should know that if our image is rigid, then this number is always going to be the cardinality of X for all J. But when this X happens to be a digital cycle, then this number is going to be 0 for all J. But in this case, this number is a constant because it's always this, or it is always this for all J. But we have this result that if this sequence is a non-increasing sequence, what I mean is by this is that when we increase the number of identities, then the number might shrink. So now we'll move to the last part of this talk, which is talk about digital Lefschetz number and approximate fixed point. And I will start with just a definition what a Lefschetz number is. If you can remember, as I gave an overview of what Lefschetz theory is all about. What Lefschetz theory tells us that he has a number which he defines almost similar to how we define this number. And if that number is non-zero, then we know that we will always have a fixed point for any mapping that is homotopy to that mapping in question. So here we just allow n to be the maximum dimension of any simplex in X. What I mean by simplex is they are the building blocks of the digital image, where the 0 simplex is just a point, and the 1 simplex is just an edge, and the 2 simplex is just a triangle field. So this number, what it says is that it is nothing but the alternating sum of the traces of the function f star q. By f star q, I mean the induced homomorphism by the homology groups on the digital image X. So there is a classical result called Hopf-Trace formula, which tells us that the alternating sum of traces of fq is the same as alternating sum of the traces of f star q. And because of this result, we are going to just consider our Lefschetz number to be alternating sum of the traces of fq. What I mean by fq is just a chain map, which is a map from chains to itself, from a q-dimensional chain to itself. And for example, we need to know how to calculate these numbers. And one of the trivial example is that of a constant mapping. If we have a constant mapping, for us to get the Lefschetz number of constant mapping is always going to be 1. Why is that? Is because the trace of this chain, that is the zero chain, is always going to sum up to 1, and the higher dimensional one will always vanish, and that means they are going to be 0. So when we sum it off, we'll end up having the Lefschetz number of a constant mapping to be equals to 1. So now, before we move to the next example, I would just like to introduce this definition we call simplicial Euler characteristics of X, which is also defined also in a similar way, that using the Hopf-Trace theorem. Instead of finding the homology groups, we will count the dimension of the chain groups, and this will help us find the Lefschetz number of an identity mapping. And you can see that the identity mapping has a Lefschetz number equals the simplicial Euler characteristics. And why this is true is that because the identity mapping will fix every q-dimensional simplex, and if we view any q-dimensional simplex as a matrix, then the identity, so the matrix will be nothing but the identity matrices, and if we sum it up, it will give us the number of q-dimensional simplices we have, and thus we will have the Lefschetz number equals to the Euler characteristics of X. And this result tells us that if we have two functions fg that are strongly homotopic, then they will have the same simplicial Lefschetz number. Or in other words, we say simplicial Lefschetz number is strong homotopy invariant. Now we move to some other additional examples. In this example, we are going to consider our function to be the 180 rotation of our image x, and by definition, we know that this is two-dimensional. So by definition, the highest dimensional simplex we might have here is 2. So therefore, we have this summation from 2, 0 to 2 of this set. And how can we calculate this this chain complex? They are matrices. They are just matrices. And the way to do that, for this first one, F0, we are going to consider zero-dimensional simplices. And by zero-dimensional simplices, I mean the points. So here we have 6 points. So therefore, we are going to list them here, and we are going to list the other 6 points here. So we will check where this function takes a takes a point. For example, if I consider only this point y0, and if I do the 180 rotation, if I rotate it 180 degree, then this function will move to this function y, and therefore that is why we have the first line going to this y3. And similarly, this will move. When we do it, this will move here, and that is why we have this, etc., etc. So when we do for the one-dimensional simplex, we are going to consider the edges, but in this case we have to define some kind of direction for the edges, so that it will be easy for us to take notice of what happens to the edges when we do the 180 rotation. And if we do the 180 rotation of this function, this edge here will become this edge, and that's what gives us that this edge E0 will be E3, E0, E1, E2, E3. That's why we have 1 there. And if we do for this edge will come to this point here, and that means this E1 will move to E4. That means E1 will go to E4 continuously. And the last one, which gave us -1 here, is this edge. And because when we do the direction of this edge goes upward, but when we do the 180 rotation of the image, the direction will the edge will remain, but its direction will change, and that's why we have -1 here. So when we sum when we get the traces of this mapping, and before that, for the two-dimensional ones, we have 0 two-dimensional simplices, so therefore the matrix is a 0 matrix, and if we take the trace will be 0. The trace of this mapping is going to be 0, and we have this, and the trace of this is going to be -1, and if we multiply, we end up having the Lefschetz number equals to 1. So similarly to this, but one interesting thing we found that is that if we don't even need to look for these matrices for us to know what the Lefschetz number of any function is. The simplest idea is that when we do this mapping, we can observe that it's like this trace is counting the number of those zero-dimensional elements, simplices that are fixed, but in this case none of them is fixed, which means that this is 0. But in this case, one of them is fixed but in opposite direction, which gives us -1. So that's here we are going to apply the same reasoning to these two examples. If we do the same function 180 rotation, we just rotate the image 180 degree. When we do this rotation, the zero-dimensional one will only be this. All the other ones will be fixed, except this x12, x12, or I can call it x12. And because this x12 is fixed, we are going to have trace of this to be equals to 1. And when we do this 180, the one-dimensional edges all of them will move. So therefore, the trace will be 0. And in the case of two-dimensional simplices, we don't have any. The matrices is going to be 0 matrix, and the trace is going to be 0, and we end up having this to be equal to 1. But, and also for this example, when we have this 180-degree rotation, we can see that when we do 180-degree rotation, all these points will go up here, and those at the top will come to the bottom. That means all the 0-dimensional points have been shifted by the function, and therefore this trace is going to be 0. And also, when we look at the one-dimensional simplices, this one-dimensional simplices will come here, this will come to this side, the two will interchange, and which means that all of them have moved, and therefore the trace is going to be 0 in dimension 1. And for dimension 2, we don't have any two-dimensional simplex, and because of this we have a 0, and the Lefschetz number of this function is going to be 0. So what are we going to do with this Lefschetz number we are defining? The aim is for us to utilize this simplicial Lefschetz number to tell us about the existence of fixed point. And we found out that whenever this simplicial Lefschetz number is non-zero, then we can always find a simplex that is fixed by the function f. And if this happens, it tells us that either that function has a fixed point, or that function has at least 2 approximate fixed points. And we also find out that for any mapping that is strong homotopic to this function f, then they will have the same Lefschetz number. This is true because we know that the simplicial Lefschetz number is strong homotopic invariant. So therefore, if a function f has a non-zero Lefschetz number and it's homotopic to function g, and if f has fixed point and at least 2 approximate fixed point, then g also will have at least f fixed point, or it will have at least 2 approximate fixed point. Yeah, and also here we consider if what will happen if we have a function that is homotopic to identity, and here we doesn't know what the Lefschetz number is, but we know that the simplicial Euler characteristics of that matrix, of that image is non-zero. Then by this theorem, or by this corollary, we will end up having either a fixed point or at least 2 approximate fixed points. Another situation we consider is what will happen if our X is strong contractible. That means it is strongly contractible to a constant mapping, and in that case we know what Lefschetz number of the constant mapping is, which is 1, and it's non-zero. So therefore, by corollary 4.6, we will end up having either a fixed point or at least 2 approximate fixed points. And one example I will give is, if I mean me to come back to this, for example here, when we calculate the Lefschetz number of this function, right, we end up having this to be equal to 1. And by that theorem, we know that we are going to have either a fixed point or an approximate fixed point. And the approximate fixed point is this. And I think I forgot to mention what an approximate fixed point is. An approximate fixed point is just a point that is either close or equals to, it is either adjacent or equals to the image of that point. So in this case, we know that when we do the 180 degree rotation, this point will shift here and the y will come here. So that means the function y1, so f of y1 is adjacent to y1 and f of y4 is adjacent to y4. So therefore, in this case, we have 2 approximate fixed points, although we don't have a fixed point. But in this example, this is non-zero, right? So we expect to have either a fixed point or an approximate fixed point. But in this case, we know that this is already fixed. So therefore, we see that we already have a fixed point, approximate fixed point. But in this case, we we obtain this to be equal to 0. So by our theorem, we cannot conclude whether we can have an approximate fixed point or a fixed point itself. So similar to what I have discussed on simplicial Lefschetz number, we also define what we call a cubical Lefschetz number. The difference between the two is that in cubical Lefschetz number, instead of using the simplices, we are going to make use of cubes, and also we have some additional restrictions. One is that the dimension of this Zn is restricted to only when n is less than or equals to 4. And also the adjacency we are going to consider here is only the C1 adjacency. What I mean by C1 adjacency is if you are in 2 dimension, it is going to be the 4 adjacency, and if we are in 3-dimensional image, we are going to consider the only to be the 6 adjacency relation. So we define this cubical Lefschetz number in a similar way as the simplicial Lefschetz number. The only difference is that instead of using the simplices, then we are going to use the cubes, and that is why we have this notation bar at the top of this cubical Lefschetz number. And similarly to what I have discussed in the previous part, using the Hoptress formula, we are going to substitute this induced homomorphism on the homology groups on the cubical chain, so that it will be easy for us to calculate what the Lefschetz cubical Lefschetz number will be. And we also consider what would be some examples. We start with that of a constant margin, and we found that the constant margin has cubical Lefschetz number the same as the simplicial Lefschetz number, which is equal to 1, and this is because of the same reasoning that the trace of this is going to be 1 when we are in dimension 0, right? And when we move to the other dimension, we doesn't have those simplices, so therefore the trace will vanish. So now we are going to also define what we call cubical Euler characteristics of X, similar to how we define the simplicial Euler characteristics. The difference I will reiterate is the use of simplices in the simplicial case and cubes in the cubical case. But here we have some examples on how can we calculate this Euler characteristics, both simplicial and the cubical. Suppose we have 2 examples, y and z. Then if we are going to calculate the Euler characteristics, we know it is going to be dimension of the it's going to be the dimension of the chains. First we have for this, if we are going to do the cubical ones, the 0 cube is the point, the 1 cube is just an edge similar to simplicial one, but the 2 cube is the whole of this, which I call A1 and A0. A1 and A0. So now I will start with calculating how many points I have here. I have 1, 2, 3, 4, 5, 6. I have 6 0-dimensional, so therefore I'll have 6. Then I will have 1, 2, 3, 4, 5, 6, 7. I have 7 1-dimensional, and I have 2 2-dimensional cubes. So if I sum them up using this formula, if I sum them up, I will have 1, which is 6 minus 7 plus 2, and I will have 1. Similarly, for this one, I will apply the same procedure. I will calculate the 0 cubes, the 1 cube, and also the 2 cubes, and I will end up having 1. But in the simplicial case, because we doesn't have this 2-dimensional one, if we do them, we'll have 6 minus 7, we'll end up having 1. And in this case, we'll have 1, 2, 3, 4, 5, 6, 7, 8. 8 minus 10, then we'll have minus 2. So you can see that these 2 these 2 Euler characteristics are different. So similar to the way we find the identity of, the Lefschetz number of identity, we found the Lefschetz number, the cubical Lefschetz number of identity is the same as the cubical Euler characteristics of identity. And the beautiful thing about this cubical Lefschetz number is that it is homotopy invariant. That means for any two functions that are homotopic, they will have the same Lefschetz number. Example also with this, similar to the way we calculated it. Maybe I think I will just rush up. The only thing that we keep in mind is that in this case we are going to have two cubes, and in that case we are going to have this to be non-zero. We know that in simplicial case it is 0 because we doesn't have two simplices, and in this case we have two cubes, so therefore we are going to have this matrix. We have two of them, therefore we have A0 A1 A0 A1. But when we do the 180-degree rotation, this A0 will come to this A1 and A1 will go to this A2, which tells us that A1 is moved to A1 and A2 moves, sorry, A0 moves to A1 and A1 moves to A0. And if we take the trace, it's going to be 0, and it does not change the Lefschetz number. We end up having 1. So similar to this also, here we doesn't have 0 cubes, so we expect to have the same similar Lefschetz number, the simplicial Lefschetz number. But in this case, here this is one example where the two simplicial Lefschetz number on this particular example are different. If you remember that when we do the simplicial Lefschetz number on this, we end up having 0, but in this case the cubical Lefschetz number, we end up having this to be equals to 1. And where we got this one is when we do the 180 degree rotation, this cube will remain where it is in the same direction, and that will contribute to the Lefschetz number. That will contribute 1 to the Lefschetz number and end up having the Lefschetz number of that function on this image to be equals to 1. Yeah, similarly, we are going to also consider, the target is to consider studying fixed point. But it happens that although we have for any cubical Lefschetz number that is non-zero on an image X, we can always have some cubes that are fixed, but this does not guarantee us to have a fixed point, or also does not guarantee us to have the approximate fixed point. But we found that there is some more restricted notion of fixed point. We call it n approximate fixed point, and this is what this Lefschetz number is giving us. And what we have is, if this is non-zero, then we either have a fixed point or at least two n approximate fixed point. And moreover, any mapping that is homotopic to F, then we will have either a fixed point or at least two n approximate fixed points. Also, if we have the function F to be homotopic to identity, then an cubical Euler characteristic is non-zero, then that function will either have a fixed point or at least fixed point, approximate fixed point. Also here we have this to be equals to contractible image, and if it is contractible, that means I can contract it to a single point using the homotopy. Then I will either have a fixed point or at least an approximate fixed point. So before I move on, here we know that we have this to be non-zero. In the other case it is 0, so we cannot conclude what we have, whether it is fixed point or it is approximate fixed point. So, but here that we have this Lefschetz number to be non-zero, then we know that by that theorem, we are going to either have a fixed point or we are going to have at least two n approximate fixed point. By n approximate fixed point, I mean the point which will have n distance between itself and its image. And when we do this 180-degree rotation of this image, this guy will move to this will move to this will move to this, and x z6 will move to z2. So you can see that each one of them moved 2 times. 1 2, this move 1 2, this move 1 2, this move 1 2, in this fashion. And this tells us that we have existence of 2 approximate fixed points. So the main thing I would like to just notice that from what we can see between simplicial Lefschetz number and the cubical Lefschetz number is that the simplicial Lefschetz number gives us a better fixed point result. Why? Because it gives us a closer notion to the fixed point than the cubical Lefschetz number. But the cubical Lefschetz number seems to work better in terms of homotopy invariance, because we only need the functions to be homotopic so that we will know if they will have the same cubical Lefschetz number. But in simplicial Lefschetz number, in simplicial part, the Lefschetz number only tells us we will be able to know if 2 functions have the same Lefschetz number only if we have additional condition on the homotopy, which is a strong homotopy notion. Here we have another example of a map which we call antipodal map, and this mapping will have a Lefschetz number on 0, and therefore we will have an approximate fixed point. So another thing is we want to just classify what the Lefschetz number, both Lefschetz number will be on the digital cycle of endpoint. And we found that the simplicial Lefschetz number for any digital cycle of any number n is either going to be 0, 1, or 2. And but the cubical Lefschetz number is equals to 1 only if n is equals to 4. And otherwise, it is either going to be 0, 1, or 2, similar as the simplicial one, the simplicial case. We are going to make use of this in the next few slides to come up with some nice results. So, but here we are going to just recall what is the relationship between these Lefschetz numbers and the number of either fixed point, an approximate fixed point or approximate fixed point. And we found that the absolute value of this Lefschetz number is equals to k. If the absolute value is equals to k, then there are at least k fixed simplices by our previous theorems. And if we have k simplices, then it tells us that we have at least k distinct approximate fixed points. And similarly, if we have the cubical Lefschetz number to be its absolute value to be equals to k, then there are at least k fixed cubes. And if we have this k fixed cube, then we'll end up having we will have at least k number of distinct n approximate fixed point. And due to this, as a corollary to this result, we found that the absolute value of this is a lower bound for the number of elements in the set. It's always less than or equal to the number of elements in the image X. Similarly, in the cubical part set. Now consider this example. By this example, if we are going to consider identity mapping on this, we know that the identity mapping would just be the Euler characteristics of the set X. And if we do the calculation, we end up having -2. And also, we end up having -2, which tells us that this identity is strong homotopy to some mappings that has 2 fixed points. But in this case, the cubical Lefschetz number, which is the same as the cubical Euler characteristics, is going to be 0. How? Because it is 0, then it tells us that we have some function that will have 0 fixed point, and that function is this. The function is as follows. what we are going to do is we are going to contract this leg, and to contract the arms of this robot. And if we do that, we'll end up having this picture, right? So we are not going to leave it like that. We are going to rotate it. If we rotate it 180 degree, then all this point will move, and we know that none of this this type of function does not have any fixed point, and this function is strong homotopy. Sorry, is homotopic to this identity mapping. We also consider one property of these Lefschetz numbers, and that property is called the commutativity property. And what I mean by this is that if I have a composition of two functions f of g and it is commutator g of f, then they will have the same Lefschetz number. Also similarly for the cubical case. And also we have these two results that will help us in the coming slide. That if we have a function for, on a self-mapping x, and we have a function g from x to y, which is digitally strong homotopy equivalence with strong homotopy inverse h from y to x, then the Lefschetz number of f is the same as the Lefschetz number of this composition. Similarly, we have this in the cubical part. So we now define one notion of a reduction of a digital image, and by definition, this is what a reduction of a digital image is. We call a digital image Y is said to be strong reduction or simply reduction of an image X if X and Y are strong homotopy equivalent, or simply if they are homotopy equivalent, and the number of elements in Y is less than that in X, then that is the condition that will guarantee that Y is a reduction of X, whether strong reduction or just simply reduction. By if we cannot have any other reduction of X which has cardinality less than Y, then we say that Y is a minimal strong reduction. An example of this is this. Suppose we have this image X, and we have this X star, and we have X prime. This image X, if we use homotopy on the identity, we can be able to, if we use strong homotopy, we can. This is the list we can reach using strong homotopy, and this is the list we can achieve when we use the ordinary digital homotopy. And you can see that the number of elements, we have this inclusion that the number of elements in this homotopy is less than that. The number of elements in the reduction is less than that of strong reduction, and that of strong reduction is less than the number of elements in X. And one example we can consider is that we want to calculate the Lefschetz number of this guy. So because of this reduction, we don't even have to look at this to calculate its Lefschetz number, because we know this identity is homotopic to this, and if it is homotopic to this, then we know cubical Lefschetz number is homotopy invariant. Then we can just find the Lefschetz number of this simpler image instead of for us to go with this complicated structure. So, but it happens that this is like a cycle that has many points, which is not 4, and by our previous theorem 4.16, the Lefschetz number of that will be either 0, 1, or 2. But whereas this term is not a cycle, so we cannot just easily calculate it. but we know that this is strong homotopy to this, and if it is strong homotopy to this, we think this will be easier to get its Lefschetz number than to calculate the Lefschetz number of this. And if we take the identity in this case and we calculate its Lefschetz number, it is going to be -2, and that tells us that this also has a Lefschetz number -2. Now we define what we call the spectrum of Lefschetz number, and this spectrum is going to collect all the number of all the possible Lefschetz numbers of functions on the digital image X. Similarly, that of cubical, which we call spectrum of cubical Lefschetz number, or simply cubical Lefschetz number spectrum. And for example, if you want to calculate the spectrum of cubical Lefschetz number of this map, is going to be either 0, 1, or 2. So therefore, we know that we have a Lefschetz number, a function with a Lefschetz number 0, a function with a Lefschetz number 1, and a function with a Lefschetz number 2. And also, we, unlike the homotopy fixed point spectrum and the coincident point spectrum, we found that this spectrum of simplicial Lefschetz numbers, the cubical one is homotopy invariant, and the simplicial one is strong homotopy invariant. And as a remark, we also note that if for any element in this spectrum, this element is always less than or equals to the number of element in X, and the negative of the number of element is always less than or equals to that number M. Now we want to also look at the relationship between the Lefschetz numbers and the homotopy spectra of the approximate fixed point. And the way we define it is that this will only collect all the number of n approximate fixed point of function g that are homotopy to f, and this will calculate the approximate fixed point of function g that are homotopy, that are strong homotopy to the function f, which we call strong approximate fixed point spectrum. And what we have is, we have this proposition that if this term is a homotopy and approximate fixed point spectrum of X, then the absolute value of the cubical Lefschetz number is a lower bound for the homotopy and approximate spectrum. And similarly, the absolute value for the Lefschetz number, simplicial Lefschetz number, will form a lower bound for the strong homotopy approximate fixed point spectrum of the function f. So this comes to the end of this presentation. The other one is just the publications and the conferences I attended, then acknowledgement, and also acknowledgement to people that gave me a chance to visit them and stay with them and share research ideas with them, and for all their kind support during my 6 months stay. Thank you very much. Any question?
Any question? Okay, any question? สอบเด็กอยู่ก็เลยอยากรู้ก็เลยโอเคเดี๋ยวคุยอีกทีเดี๋ยวคุยอีกทีเดี๋ยวเรียกส่งไม่ถามดิก็เลยไม่เห็นมีอะไรมาเลยมองน้องเงียบโอเคเดี๋ยวแป๊บนึงเดี๋ยวผมถ่ายงานดีก่อนโอเคthere are any question Professor Chris say that he is disconnect in on slide 31. He have some question. You can see in message.
But I
You
don't
can
know
click in the message
what's
and
the question.
this question you can answer this question.
All right. Slide 31.
Yes. But Professor Chris left because he is disconnect on that slide.
Oh, I don't know. I'm sorry.
Yeah, he says sorry for I don't know. Maybe also it's a midnight for him.
Yeah.
Yeah, you can see in the slide and right hand side the question.
The question.
Yeah, you click in the conversation is here. In
Okay. Yeah. Yeah. Recording has started. I know exactly where you were because I was making small notes on your slide. On the maximum dimension of any simple one.
it's for comment from Professor Chris.
Yeah. Okay. Yeah. I've seen it. I've seen it. Yeah. Thank you.
Okay. Some another question.
Room for improvement.
You see is you use some leadership number. I want to know is you leadership number is at the same is the leadership constant in a metric frequency theory at the same sense.
I think it is always called Lefschetz number.
But I saw you define some is contraction, some name of contraction in a digital space.
On the slides.
Yes, some slide I remember is a slide for look like contraction and leadership number.
On the metric part or the digital topology?
On digital topology.
Okay, let me show the slides again. Maybe
I mean, how to compare between leadership constant and leadership number.
Oh, Lefschetz constant and Lefschetz number.
Yes.
I think they are two different things because the Lefschetz constant looks like a contractive condition.
Yes.
But the Lefschetz number is just like a number that a function gives on a particular space. And if that number, the way he defined it, he used some homology, but I think the way we define it in this case is that we are going to make it easy for us, and with the help of one classical result called Hopf-Trace formula, because it will be easy for us to calculate the chains, and the chains we mean the dimensional chains. If we say zero dimensional chains, we mean only the points. So we can be easily calculate the chains, because if we say we are going to do the homotopy, is going to be a little bit trickier, difficult to do. I think they are different. They are different things.
Oh, I think it's maybe some party related. It's
I know they are not related.
You're back to your slide in the main result of leadership number.
Okay.
On your slide, in the main result of leadership number.
The fixed point result.
Yes.
I think this is it. Yeah.
I see in the strong contactable digital image. It look like contraction.
It is not a contraction in the sense of distance. It's just that if I have a function, I can change the function to a single point. I will collapse the function to a single point. Yeah.
Look like it's a contact reduced to 1 point.
I think I cannot say contraction, because what contraction is doing in, like, the Lefschetz constant will check the distance between the images of the function and see if it will be contracting with the distance between the free images. But in this time, I have a function on X.
Yeah.
If this function, I can continuously move the function to a 0 point. Maybe I think what I will do is I will give an example
Yes.
of a function that contracts to a single point. Maybe it will be easier for people to understand.
Okay. Okay. Also, there I have some question from
All right.
audience and student. You can ask him. Okay, all students, are you sleeping?
No.
Not sleeping,
Yeah.
sir.
No, we are not sleeping, sir.